Final speaker before the break, speaking on coding techniques in JPEG XS for efficient production and contribution, Siegfried. Thank you.
Yeah, thank you and good afternoon. My name is Siegfried Frösel from Fraunhofer IIS. You may wonder why I'm speaking about JPEG. So we are in a video conference here, but in some rare cases, also some JPEG image codecs are used for video coding. And JPEG XS is one of these codecs. So what is the difference? Typically, in a video coding system, you want to improve the coding efficiency as much as possible. But there are some use cases like production or mezzanine coding or contribution where the coding efficiency is not the highest priority. And for this reason here, we concentrated more on the lowest complexity, on minimizing the latency and also minimizing the computational and memory resources. And the application areas for such kind is, of course, video production and contribution, or some in-house distribution or in-car communication, so to name some of the use cases. You see on the right-hand side some examples where you see that it is possible, of course, to reduce the bandwidth by a magnitude of order to transmit video data over Ethernet lines, and that's the main goal here for the JPEG XS. We want to replace SDI or uncompressed video transmission, and this falls into this category NDI, SDI replacement, or SD2110. And we want to have a good compromise between the quality and the complexity by preserving the lowest latency. And I have learned here at this conference that originally I always say we want to achieve ultra-low latency, but I think in this context here it's more real-time latency. Latency in our requirement is that we have a maximum latency algorithmic-wise of 16 lines of an image on the encoder side, on 16 lines on the decoder side. And with an FPGA implementation, you can reach such very low latency. The typical compression ratio is only 2:1 to 10:1. However, the requirement is to have a visual lossless quality, means we also defined a specific quality test, a so-called flicker test, where we are showing the original and the compressed, decompressed image several times per second, so that you can exactly see what changed by the compression, decompression. So the architecture is shown here on this slide. So typically we start with a normalization to 20-bit. So this allows us, with the precision we have, to compress components up to 16-bit, visually lossless. For mathematically lossless, we have to go up to 24 bits, but there is a special handling for this as well. We use only a simple RCD color transform for the RGB images, similar like in JPEG 2000. We decided also to use a 5.3 wavelet filter, not the 9.7 wavelet filter in JPEG 2000, but the 5.3, and with only maximum 2 vertical decomposition levels and 5 horizontal. Otherwise, we could not achieve the 16 lines latency. And then we make a slicing of the transform coefficients, and we make a weight distortion calculation only on this slice. So that means we are able to transmit already after this 16 lines the data to the transmission line. As I said, in hardware, the end-to-end latency can be 32 lines. In software, even with a grabber and a playout card, it can be below 200 lines. And however, you need a special hardware, of course, to achieve this, because then you need a subframe access to capture the data and to play out the data. And we are also coding 4 coefficients at once with a kind of envelope coding or MSP coding. and then we make an entropy coding of the underlying bits. And if necessary, we also transmit only the raw data. We are at such a high quality that sometimes it's better to transmit the raw data instead of trying to entropy code the raw data. Here you see some of the test images we used, some representatives of the test data set. On the left-hand side, you see an image and a sequence which is called ARI alexadrams. It's a natural image captured by a camera. On the right-hand side, you see a screen content with mixed text and video images. And then we, of course, tested how good is the quality and what is the drawback to use reduced complexity and limited number of decomposition level on the transform. You see the best quality here is for both images full JPEG 2009-7 transform and a full way of encoding. Nevertheless, with the 5.3 wavelet transform and the reduced number of vertical decomposition levels, we reached also a good quality. And for natural images, it doesn't give really a difference if you code the full image or if you code only one slice of the image with JPEG XS. If you use the JPEG 2000 with the 5.3 in the same configuration, you have here a worse quality. For the screen content, it's a little bit different because JPEG 2000 has a very complex context modeling, and of course, then for, let's say, the screen content, the quality for the JPEG XS drops, but we will see how we can affect this. With this design, we can reach ultra-low, or I would say real-time latency, and we have realized this in a prototype implementation. It's a kind of waterfall implementation. So we combine multiple slices into one slice group, and then we process a slice group per thread. And with this configuration, for example, you can use on an HD video 5 to 7 slices per thread and 6 to 12 threads. And then after starting the first thread, you are waiting for receiving the next data on the capture card, and then you start the next thread and so on, and the same on the decoding. And as I said, with this implementation, you can reach an end-to-end latency of about 200 lines. For the performance, you can say we are so low complex that you can have 60p HD decoding on one core of an x86 processor. For encoding, it's a little bit more. What is the beauty, of course, of JPEG XS, that it really is the number of processing time is linearly with the number of slices, so that means it depends only on the amount of data you want to process. And here you can see the slices per slice group and the processing time per slice group, and it's then more or less your choice how many slices you want to process in one slice group, or how many threads you want to generate, and what latency you want to achieve. Then we started with a second edition of JPEG XS. Here we concentrated more on a bias-CFA compression. Here we replaced the RCT by a linear point transform and a so-called star Tetrix transform. And on the diagram, you will see on the bottom a simple RCT plus a difference between the green RCT-T And with the star T13 transform and the nonlinear point transform, we achieved up to 4 dB better quality. And the star T13 is more or less a lifting scheme where you compute the CPCR, the luminances, the delta of the luminances, and the average luminance, and you use then a 4-component wavelet transform afterwards. For the third edition, we now addressed more the issue that for the screen content we have a not so good quality. Maybe if I go back a little bit, sorry. Yeah. Or let's first explain how it works. So in principle, what we added is here now a frame buffer. It's similar like in MPEG, so we added a frame buffer in the encoder loop and the decoder. Not to make a motion estimation and motion compensation. We want to keep the minimum complexity and the latency. That means we use the frame buffer only so that we can predict the image either from the previous frame or from the actual frame. So, and we also use the frame buffer in such a way that we can compress the frame buffer to even reduce the memory requirements. And then we can decide either if we want to make an intra or residual coding, and dependent on either a group of coefficients or on a complete wavelength band. So that means we can say, okay, for 8 coefficients we make a residual coding, and for the next 8 coefficients we make an intra coding. And here you can see now the test sequences we use. So on the left-hand side, you see it's more or less a static background, and people who are make music on drums. And on the right-hand side, you see screen or mixed content. But what is critical here on the right-hand side is that you will also move the windows on this. What is the result now? If you look to the screen content, sorry, on the Alexa drums, so natural content, you have only a small improvement by around 2 dB. That's mainly because of the more or less static background. And if you have, of course, a complete moving image, then there is no improvement. On the screen content, however, here you see on the bottom the classical JPEG XS first edition. And now with the frame buffer dependent on the number of bits in the frame buffer, 3, 6, or 9 bits per pixel, you can significantly improve, of course, the screen content. Now we make a look on the sequence itself. What is the quality on individual frames of the sequence? If you look to the Alexa drum sequence, then it's more or less the improvement equally distributed over the complete sequence, because the background does not change and the improvement is there. For the screen content, however, you will see that dependent on the change of the screen content or moving windows, you have a drop, of course, of the quality, which recovers after a while, because then the frame buffer gets closer and closer to the original image, and then you can even achieve up to mathematically lossless quality on the screen content. What we also implemented is a kind of gradual refresh, so we have not a classical I frame or B frame. So that means we regularly update parts of the image so that we have a continuous refresh on the images. Important for this is, of course, that we also not developed the core coding system. So we also made a complete ecosystem for file format, transport formats. We created also MPEG transport stream amendment, and we worked on standardization for RTP for JPEG XS to allow SD2110 transport, and there are in the moment also several technical recommendations from BSF and for the orchestration of JPEG XS with SD2110 available. And that's the overview. So we are in the moment in the final steps of the third edition, and the summary, the JPEG XS is mainly designed for, let's say, special use case for video contribution or in-house distribution with very low complexity and ultra-low latency. Thank you for your attention.
Thank you. We have time for a question from Siegfried. Yes. I'll come this way. It's probably faster than getting out.
Hi, I have a question about contribution. So being that JPEG XS is so lofty, it's such a heavy protocol, have you tested like with cloud contribution as well as maybe testing with some I'm trying to think of like a football game or things like that? And have you done any of that with these any testing with those types of things?
Yeah, sure. Though there are several aspects, of course, what I have shown here are only some special representatives of the test images. We have, of course, also the classical crowd run, for example, as a test image sequence, or other test sequences from the EBU, which we are using. And even today, AWS is offering JPEG XS for transmitting of content to the cloud, and many customers already using it for live transmission here.
Okay, and I think that's it for questions. Another round of applause for Siegfried.
Thank you.